So our next task will be just try to convert this expression, the I component, to a total divergence, the derivative of something. Now you see, since they just both look quite similar, the part that contains the electric field and the part that contains the magnetic field, I will just look at one of them. If we look at this one, if we can convert it to an expression that is the divergence of something, well, this part is exactly equal to that one. Just replace the electric field with the magnetic field and epsilon 0 with 1 over mu 0. So let's look at that part and see if we can convert it to the divergence of something. Now you see, if we cannot convert it to the divergence of something, we cannot claim that the linear momentum that we defined in this way, in that way, is conserved. If we want to make such a claim, we have to make sure that the total time derivative of that conserved quantity within a given volume, it should be written in terms of a surface integral. That is how we identify conserved quantities. So let's look at curl of E cross E plus E times the divergence of E. And I would like to write down the I component of this. Well, the I component, let's just open up the cross products, etc. So this is the I component of that cross product will be epsilon I j k, the curl of E, the j component ek, plus ei. The divergence of E is nothing but the derivative with respect to xj of ej. I just wrote everything in terms of the indices. Now let me also write this curl as in terms of its components, epsilon I j k, epsilon j l m, del l e m, ek. So this part is the j component of the curl of E. Well, the other part, there is nothing to do. Now I have the product of two epsilon tensors. I can just write it out. This will be, well, there's a minus Kronecker delta I L, Kronecker delta K M, minus I M, K L, del L E M, E K, plus E I, del I E J, del J. Sorry, this is. Well, this product with the minus sign is nothing but the product of two Levi-Civita tensors. Now let's open up. So this is del I ek multiplied with ek. This is my first term because this tells me, this Kronecker delta tells me that wherever I see an L, I should put an I. L is over here in this term. So it becomes an I, and this tells me that wherever I see an M, I should put a K, or wherever you see a K, you should put an M. So that is, M becomes K, this is EK. Still there is a sum over K, which I'm not writing explicitly. Let's look at the other term. That term tells me that wherever I see an M, I should put an I. This is del LEI. And the second Kronecker delta tells me that wherever I see a K, I should put an L. EL plus EI del J EJ. There's a minus side, right. It is this minus over there that I forgot. Now there are many indices, most of them are dummy. So let's just give the same name to the dummy indices. Here the dummy index is K, here it's the L, here it's the J. Let me call all those dummy indices J, so that I will see if the certain terms are equal or not. This is equal to minus del I EJ times EJ plus del J EI times EJ plus EI del J EJ. This is equal to minus del I. Well, this is, I have two EJs. It's nothing but the derivative of EJ squared. 1 over 2 EJ squared. Derivative with respect to xi. If you look at these terms, I have EI times EJ. The first term is the derivative of the EI. The second term is the derivative of EJ. This is nothing but the total derivative of EI times EJ. Plus del J of EI EJ. Well, this thing I can, well, you see, it's already a kind of a total derivative. This is the total derivative of something. This is the total derivative of something else. Let me just put it in a form that will look nicer. Correct. This is equal to minus del I 1 over 2 E squared plus del J EI EJ. Well, I would rather write all the terms as the derivative of the same, derivative with respect to the same thing, del J. I will do this trick. This is equal to minus del J Kronecker delta IJ 1 over 2 E squared. Because this Kronecker delta, I'm summing over J, it just tells me that wherever I see a J, I should put an I. So it is the derivative with respect to xi. Plus del J of EI EJ. This is equal to minus derivative with respect to xj of Kronecker delta ij of 1 over 2 E squared minus EI times EJ. You see, this thing over there, for a fixed I, it has one J index, one free index, which can take values x, y, and z. So for each I, this is the J component of that vector. And we are taking the J component of that vector, taking its derivative with respect to xj, but that is nothing but the divergence. So for each I, this expression is nothing but the, for a fixed I, let's say you choose I is equal to x. You see, we are looking at the conservation of the x component of linear momentum. In that case, I is fixed, it is x. So this is the three components of a vector, the j component of that vector. We are taking its derivative with respect to xj. So that's the divergence of a vector. For x, that's the vector, that's the divergence of a vector. But that is what we wanted to start with. Let's write down everything together. So here, we started with this expression. Now let me just copy all of it. This was our expression that we had derived. And now we see that this volume integral, we can write in this form. Let me take the minus sign out. That derivative with respect to xj of epsilon 0 times Kronecker delta ij 1 over 2 e squared minus ei ej plus 1 over mu 0 Kronecker delta ij 1 over 2 b squared minus bi bj. So that whole thing is nothing but the divergence of a vector for each I. And this vector for each I has the j component given by epsilon 0, or let's say Kronecker delta ij of 1 over 2 epsilon 0 e squared plus 1 over 2 times mu 0 b squared minus epsilon 0 ei ej minus 1 over mu 0 bi bj.
Yani hocam bir vektör var. Bu vektörün komponenti de başka bir vektör.
You can also interpret it like this. Don't say it a vector. We have this quantity called a tensor. A tensor can be interpreted as it's a vector whose components are themselves vectors. That's an alternative way of interpreting it. And with this definition, now we have, you take the I component of the mechanical momentum, the I component of the electromagnetic momentum, you take the total linear momentum within a volume, and the rate of change of the mechanical momentum, of the linear momentum within that volume is equal to minus some surface integral of Ti. For each I, we have a vector. And this vector, for each I, it has these components. Which one? Mm-hmm. You see, I say that for each I, this Ti is a vector. And that vector has components. The j component of this vector has this expression. You see, one expression already looks familiar. So is it familiar to you?
Bunda bir gariplik var hocam. 1 bölü 2 mu 0 olması.
Mu 0 is down. You're right. Yeah, that's the energy density. So a kind of momentum flow also contains the energy density. Well, most of the time we just call it Tij. Rather than using this weird notation, this notation you will not see. It's just a Tij.
Artık vektör olmadı aslında.
You see, certain things are still vectors. You see, Tij, if you fix I and just let j to have x, y, and z, then for a fixed I, x, y, and z components of this Tij, they form a vector.
Ama enerji vektörü değil.
Of course, you see, the components have dependence on energy. You see, you can talk about velocity vector, then say that, okay, the velocity vector of such and such a particle is in this direction 5 meters per second. Okay, 5 meters per second doesn't have a direction, it's not a vector, but it's the component. The components are not vectors. The components form vectors. So here, for each I, I'm saying that this quantity is a vector. This quantity is a vector for each I. Then I have to know a way of calculating its components of that vector. The components of a vector are not vectors. So I have this Ti vector. Its J component has this expression which has relations with the energy density. It's related with energy density, which is not, it's the number, but components need to be numbers anyway. If you want, you can just show this quantity as a matrix. So it has two indices. It will be a 3 by 3 matrix. Txx, Txy, Txz, Tyx, Tyy, Tyz, Tzx, Tzy, Tzz. It's just different ways of showing the same thing. The trace is interesting, by the way. If you look at the trace of this object, this is Txx plus Tyy plus Tzz, which is nothing but Kronecker delta Ij, Tij. Well, we already know what Tij is if you multiply it with Kronecker delta. Well, what is the Kronecker delta Ij squared? It's 3. So if you multiply this expression of Tij with Kronecker delta Ij, you get 3 times the energy density. Then these terms, this is epsilon 0 times, this becomes E squared, and that becomes B squared. So minus epsilon 0 E squared minus 1 over mu 0 B squared. If you just subtract it, you just get 1 over 2 epsilon 0 E squared plus 1 over 2 mu 0 times B squared. So this so-called energy momentum tensor or stress energy tensor its traces are nothing but our energy density. So you see, don't forget our starting point. What is our starting point? Our starting point is the rate of change of the I component of linear momentum. So I is fixed in our derivation. So we fix I from the beginning. If you want, just forget about the I component, because it's fixed. Now we have this expression over here. Here I'm summing over J. Here there is an expression that depends on J. Well, it will be a vector. So here I have the J component of a vector. I'm taking its derivative with respect to xj and summing over J. That is how we define the divergence. Now you see the divergence of a vector field. You take the x component, take its derivative with respect to x, the y component with respect to y, the z component with respect to z.
Hocam şimdi burada hani enerji density'den yararlandık ya.
No, I didn't use the energy density. As a result of my derivation, I just ended up having an expression that contains the energy density.
Peki buradan momentum density diye bir şey çıkartıyoruz.
We already have what momentum density is. You see, the linear momentum of the electromagnetic field is this integral. So this quantity over here is our linear momentum density of the electromagnetic field. So we already have derived it. That T basically describes how that momentum density flows through our surface. That T is the flow of the linear momentum density.
O zaman T pointing vektör mü?
T plays the role of pointing vector. You see, what pointing vector was, pointing vector described the flow of energy. So we have a system that has some energy density, and this energy density is flowing around. So that flow around is described by the pointing vector. But this system also has linear momentum. It has a linear momentum density, and as my system is changing, that linear momentum density is also changing. So if I am to claim that linear momentum is conserved, that change should be due to the flow of this linear momentum. And this flow of linear momentum is described by T. And each component of linear momentum has 3 components. Each momentum of linear momentum can flow in 3 different directions. So that's why T has 2 indices. So it describes how the x component flows in the x direction, x component of momentum flows in the y direction, x component flows in the z direction. It also describes how the y component flows in the x, y, z directions, and the z component flows in the x, y, z directions. All are described by our T.
O zaman hocam o hani Z component X, Y, Z direction'da nasıl hareket ediyor diye şey dedik ya. Zaten Z component diyoruz. Bu Z component X, Y, Z içinde hareket ediyor.
Yes.
Biraz garip.
It's just like in a wave on a string. Yes. You see, you have this vector. That's the momentum. That is what we call linear momentum. Well, for particles, point particles, linear momentum and velocity, they basically point in the same direction. But that is only for point particles. It need not be the case for waves or electromagnetic fields. So an electromagnetic field can have a linear momentum in this direction, but it can flow in this direction. Just like in a wave on a string. You see, the waves in the sea. The particles that make the sea, they are moving just up and down, more or less. But the wave is moving horizontally.
Alanlar olarak düşünebilir miyiz? Hani alanlar gibi, hani her defasında bir alan gibi.
I would say no, but formally, of course, yes, because areas are just ranked to tensors. Okay, so no. Okay, so at least for the discussion on this subject, no, don't think of them as areas. Other questions? So now what we had. This was equal to minus. Well, let me write it in this form. This is the A dot T. This is what we said. This is equal to minus dAj Tij. I just wrote the first line in terms of its components to avoid that weird notation. So I say we have this volume, and then we said that through this volume, the momentum is changing because the momentum is flowing. If the momentum is, this derivative is negative, that means this integral is positive, so the momentum is flowing out. Tij is the momentum flow per unit time through an area, or the momentum passing through unit area per unit time. But momentum per unit time is nothing but force. So this is nothing but the force per unit area, Tij. Well, this force, of course, has a perpendicular component. It can also have a horizontal component. It doesn't have to be perpendicular to our surface. But we can identify the pressure. If I take this force, well, Tij, you see, it's the, just if you look at the above definition, it is the momentum flow in the j direction, but the momentum is in the I direction. It's the flow of momentum in the I direction passing through the surface in the j direction. Let's look at particular components. Txx. Okay, what is Txx? It is the flow of the x component of momentum in the x direction. Right? Tyy, the flow of momentum, the y component of momentum in the y direction. Now, these are already things that should be familiar. I mean, if you have a point particle, if it has a momentum in the x direction, it is flowing in the x direction. If it has a momentum in an arbitrary direction, it will have a component in the x direction which will be flowing in the x direction. It will have a component in the y direction which will be moving in the y direction, etc. So those are Txx, Tyy, and Tzz. Now let's look at this one. Let's assume we have a surface, not necessarily in the x, y, or z direction, but in the direction n. Well, this will be nothing but the flow of the I component of momentum through my surface. It's not just the x, y, or z, it's the whatever the direction of my surface. This n is the normal to my surface. This is the force acting on my surface. So basically, I have this surface. I define a normal vector to it. We said that Tij is the flow in the j direction. So Ti, if I call it a vector, it is the flow of momentum. It's the direction of it's the vector that describes the flow of the I component of my momentum. Well, the component that is passing through my surface, I can obtain it by just taking with its scalar product with n. Just in analogy, if you have a total current density, just multiply it with the normal direction to any surface. This is the current density passing through your surface. Just like here, I take this. For each Ti, Tij are the components of the Ti vector. I'm just taking the j component, multiplying with the j component. I'm taking this scalar product. So this is the force acting on my surface. It's the I component of the force acting on my surface. force per area. It's the force, because basically this is the motion of the the flow of the I component of momentum per unit time. The momentum per unit time is what we call the force. I want to identify the pressure also. The pressure is not the force per unit area. It's the force per area. It's the perpendicular component of the force per unit area. That is what we call the pressure. So since this is the total force, the force need not be perpendicular to my surface. If I take the perpendicular component, that will be the pressure. Electromagnetic pressure, let's call it P, is equal to Tij and I and J. So this will be the pressure acting on my surface. This is the component of this force perpendicular to the surface. There is plus the other component, which is horizontal to the surface, which we call the shear. Again, if you remember your first year, we didn't really discuss it that much, but when we were talking about the elasticity, we described the pressure. Pressure was basically, if you have a volume, if you have an area, there's a perpendicular component of the force, and that force, the perpendicular component of the force divided by area is the pressure. At the same time, we were also considering, if you take this book, you can, the pressure will be perpendicular to the surface, but you can also exert a horizontal force due to the friction, and it will cause the book to deform. So this is what we call the shear. And so this is the force. There is a component of it perpendicular to the surface, which we call the pressure. There is a component horizontal to the surface, which we call the shear. Just the terminology, so that you learn the terminology also. So now this is the force or the pressure acting on a surface due to the electromagnetic fields. So they also exert pressure. So now, for example, you can calculate. Last semester you had this problem. We had a homogeneously charged sphere. And you were asked to find what is the force acting on the upper hemisphere due to the lower hemisphere.
Shear mi yapacak?
No, not shear, but no, I mean, you see the force over here, it will depend on the direction. In this case, the electric field is always radially out. Well, this is not homogeneously charged, sorry, it was a conducting sphere. Well, this system has an electric field. Well, there's no magnetic field in this case. Let's look at our expression of T, Tij. Well, there's no magnetic field, fine, but nevertheless there is the electric field. So you can just look at the components of the electric field, of the energy momentum tensor. Using those components of the energy momentum tensor, you can calculate, if you want, whichever component you like. Basically, you see this is the force acting on any surface. This one. So you already have the force. Just integrate it. Just take the if you already know that the force should be in the z direction, so you just look at I is equal to z only. So just another way of looking at the same problem. Or, for example, we will probably discuss it in more detail later on. There are these toys. So it's a vacuum inside. So in it there is a very sharp needle. On the needle there are 4 leaves. It has such a shape, in the shape of a cross. So there are 4 plates over here. One side is dark, the other side is light. I see this side is dark. So if you shine light to it, it rotates due to light. Well, the direction of rotation changes if it is a pure vacuum or not. So at least in pure vacuum, it should rotate. It does rotate. And it's basically due to, well, light has both electric and magnetic fields, and hence this T is non-zero. It has a non-zero T. It exerts a pressure. Pressure is non-zero. We will calculate this T tensor for electromagnetic waves. It's non-zero. Hence, it exerts a force or a pressure, and that is what causes it to rotate. Well, why one side is dark, the other side is not, is basically because one side absorbs the light, the other side reflects it. Reflection transfers more momentum than absorption. You see, if you just have a ball, throw it to a wall, if it sticks there, the momentum it transfers to the wall is all of its momentum. Whereas if it doesn't stick, it goes there and bounces back, the momentum it transfers to the wall will be twice its initial momentum. So that's why here one side is dark, one side is light. That imbalance between these opposing plates is what causes the torque.
O zaman hocam hani diyelim ki bu Süpermen. Bu yerden zıpladığı zaman yeri çökertir mi?
Of course. Well, in Superman it doesn't do it. It's not that realistic. But look at Matrix. In third one, it also acts like a Superman. But you see that the ground is pressed down. In that sense, it's more realistic, let's say.
Hocam sonuç TAJ dediğimiz hani kuvvetin A yönündeki komponentinin J'deki akışı değil.
Well, let's try to reinterpret it. What is Tij? We said that Tij is the flow of momentum in the J direction, the I component of momentum. So what is force? So if you just take some region of space, let's say, the force acting on this region of space will be the rate of change of momentum of this space. Okay? So if you take Tij, multiply it with the surface area, so that is because the momentum should be flowing inside, multiply with Nj. So this will be the momentum entering and integrate this over the surface area. This will be the I component of momentum entering this volume. But the per unit time. Well, the momentum change, or in a different way, just take this expression, multiply it, integrate it over this surface. That will be the change in the I component of momentum of this object per unit time. That is force. Tij itself is not real. You cannot interpret it as a force. because even the units do not match. It's the force per area. That's why we can relate it with pressure. Again, it's force per area. But you cannot say T is the force or the flow of force. If you multiply it with an area, it becomes the force. It's the flow of momentum, the rate of change of momentum. Go over the exercises in your book. There are already exercises with solutions where you just calculate them explicitly. That will help a bit, and you will hopefully get your homework also.